Hi. So we're going to be doing a lesson here today on topic 4, exponential equations and regression. So let's take a look. Now our goal is to determine the exponential function that best fits a set of data and use the function to solve a problem. Now we've done regressions before. So don't be scared. It's very similar to what we've done before. So let's take a look. Here's some information to guide us. We've discovered that an exponential function of the form y equals a times b to the x can be an increasing or decreasing function. We know that. An exponential growth function is an exponential function whose y values increase as you move from left to right across the x-axis, and it occurs when b is greater than 1. An exponential decay function is an exponential function whose y values decrease, and that's when b is between 0 and 1. We can get a scatter plot, which is a set of points on a grid, to visualize a possible trend to the data. An exponential regression function is the equation of the curve of best fit when the scatter plot looks like an exponential function. And we're going to use a technology, RTI-84, to use exponential regression to determine the equation that balances the points on the scatter plot on both sides of the curve. So let's start by looking at some examples. Excuse me. A biologist was monitoring the growth in the number of fruit flies in a controlled environment. The fruit fly population was recorded over a 5-day period as shown in the table before. So we're going to determine the exponential regression equation that best represents this data. So we have this data right here. So we're going to use some things from it to kind of let us do our data. Our day will be our x, and our y will be the number of flies. This will also be our list 1 and list 2. Now, when we set up our windows, we'll talk about how we can use the domain and range to do so. Excuse me. So let's start by clearing everything. So my y1, it's all clear. I'm going to go to stat, enter, and I'm going to enter my data in my lists. So 0, 1, 2, 3, 4, 5. That's my list 1. Those are my x values. And my y values, 71, 77, 85, 92, 101, and 111. Okay, very similar to how we've done regressions before. If you can't remember, at the back of your notes package on page 66, you can find all your steps. Okay, so we want the regression equation. Well, let's take a look first at what this looks like. So second function, stat plot. We're going to turn stat plot on. Enter on. We want a scatter plot. X list is L1, Y list is L2. And we'll do zoom 9 to set our windows. So we can see there's our scatter plot there. Now, we want the exponential regression equation. So what's different? Not much, except for your selection at the end. So go into stat and then calc and scroll down to selection. We're doing an exponential regression. It will be, oh, it's actually right at the beginning. I'm jumping the gun. Is it not? It's 0. Well, press 0. Exponential regression. So 0 is our selection. And then we'll go second function 1, comma, second function 2. And that's just to get my L1 and L2 are my two lists. And then enter. And we're going to get our exponential regression. Now here it has our y values and our y is equal to a times b to the x. A is 70.754, blah, 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 blah. B is 1.0934, blah, 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 blah. And we're rounding to the nearest hundredths. So we're going to get y is equal to 70.75 times 1.09 to the x. So I've rounded to the hundredth there. Now, using your regression equation, estimate when the fruit fly population will exceed 160. So let's put this into our y values. Vars, 5, arrow, arrow, enter. And we'll graph that. Now we want to know when the fruit fly population will exceed 160. We're still graphing here. If I go to my windows, I need to make sure that my y value is going to encompass 160, because right now it just goes up to 117. So I'm going to have to go down here, and I am going to extend my y max. So I want to extend my y max so that it's going to be greater than 160. So let's say 170. Now I've increased that, so I'm going to also increase my x max because I want to make sure that I have a value there. So I'm going to increase it to 10. Just that's an estimate based on the information provided. If I need to, I can always extend those windows again. So this is for Windows, right? For your Windows, just so that it encompasses this data. So now we're going to graph again. And we see we got a lot more room over here because we're extrapolating. So we want when our y equals 160. So we can do this a number of ways. Basically, what we're doing it graphically here. We go in here and we'll make y2 equal to 160, and we'll graph that, and we're going to get an intersection point. So second function, trace 5 for intersect, enter, enter, enter. And so using graphing, we will get y equals 160 when x equals 9.13. So that would be 9, or it says next, the nearest whole day. So actually in this case, we'd actually round up because we want to do that. There's another way you can do this as well. You can also make it 160 equals 70.75, 1.09x, and you can make this your y1 and this your y2, which is actually exactly what we've done, and we're just finding the intersection. We've got our graph there, okay? Now, the reason why we round up is because we want it to exceed 160. At day 9, if we put in a value of 9 for x, we only get 158 fruit flies. So if x equals 9, y equals 158, so which does not exceed. So you have to really think about this, and this would be a case where you don't round down. Okay, but as you can see, the exponential regression is very similar to the regressions that we've done before. Creating graphical and algebraic models of given data. So we've got another data table, and we don't know if this is, we're going to graph this, but let's look at the data to begin. So this is a population graph, and it's years since 1871, and we're looking at the population of Canada. And it says, could this data be represented by an exponential growth or exponential decay function? Well, as we notice, we have increasing values, right? As the years increase, so do the populations. So this would be exponential growth, because things are increasing. If the population was going down, then it would be a decay. Now, using graphing technology, we're going to create a graphic model. So we're going to do exponential regression. So let's just do that. Sorry, it's such a big table. And we're graphing in our years, which will be our list 1, and our population. List 1 is our X value, and population is our Y value. So I'm going to go first, and I'm going to clear my Y, and then I'm going to go in and I'm going to edit my lists. So let's clear list 2, and then we'll clear list 1. And we're going to enter this data. So we have 0, 10, 20. I wish there was a shortcut where you could just put it in by tens, but we've got to enter it all in. I mean, it could be worse. We could be doing this calculation by hand, right? 70, 80, 90, 100. So that's our X values. Then let's go over to our Y values in list 2. Now this is population by millions. I'm just going to put it in by like 2.44 as per, because I don't really want a graph that has millions in it. And I'll just be aware of that. I bet my answer will be in millions. Oops, that's 3.23, 3.74, 5.42, 7.22, 8.8, 10.38, 11.51, 14.01, and 18.24, and 21.57. Just do a quick scan, make sure that it all lines up. It looks like it's good. Looks like I haven't missed anything. I don't want to. Okay. Now we know we should just double check stat plot is on. Good. So now we're just going to go zoom 9, and it's going to graph. We get that nice looking scatter plot when we graph it, right? Now we want to do our regression to get our equation, and we're rounding to the nearest hundredth. So we're going to go stat, calc, and we select 0. Exponential regressions, second function 1, comma, second function 2, enter, and we're going to get our equation, and we get y is equal to 2.67, I will round that up, times 1.02 to the x. So this would be our expression, our exponential equation. Now, question here says, assuming the population growth continued at the same rate to 2011, estimate the population in 2011. So on our graph, if we look at our windows, 2011 would be quite a bit more from 1871. 2011 minus 1871 equals, dun, 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 2011 minus 1871. This would be 140 for our x value. Okay, so if x equals 140. So let's change our window for our x max. Let's make it 150. And our y max. It's hard to see with that growth. I'm going to actually put it up to 60, just in case. So let's graph that and see what we get. Oh, I've got to put my formula into bars, don't I? Bars. 5. Enter. Oops, I need to put it into this, don't I? Sorry. So now I've got my equation in bars, or in the y equals, and now I graph. I'm going to get a continuation of the line. And I'm looking for x equals 140. So all I have to do is go second function trace 140. So when x equals 140, y equals 54. It's 54.1, but this would be 54 million, right? It says to the nearest million. So pretty handy there. We're using that exponential equation to solve that. Okay. Example 3, determine an exponential equation from a graph. So basically, we have some points on our graph. We have our x and our y. We know when x is -2, y is 16. When x is -1, y is 4. When x is 0, y is 1. Okay, so to find the parameter b, substitute a point that lies in the curve into the equation y is equal to abx. So here's the thing. We know the a value because we have our y-intercept, right? So from this information, we know that y is equal to 1. Okay, so we want to solve for, we need to know our b value. And we also have 2 consecutive points, right? If we're going up, we're timesing by 4, timesing by 4. So y equals 1 for our a, because it's y is equal to abx. And our b, if we're going in reverse order, it's timesing by 4. So, oops, I should really kind of explain that because it's opposite direction, right? So let's think about what it's actually doing. If we're going the opposite direction, we are multiplying by 1/4, right? Times 1/4. I went the wrong way. Okay, because it's a decreasing function. So it'd be 1/4 x. Okay, and you can check that, you can test that by plotting that. And the other way you could do it is you could just substitute in values and see what works, right? You should test that. Testing this, if we have x equals -2, y equals 1/4 x, right? Because we could write it as 1/4 x. So 1/4 to the -2 equals, let's try that out on our calculator. Clear. 1 divided by 4 brackets to the -2 will give us 16. And we can test the other value there that's given. 1 divided by 4 to the -1 gives us 4. And testing our 0, we would get 1, because anything, whether it's 1/4, anything to the 0 equals 1. So that would be a way to kind of verify and test that you're doing it correctly, okay? So you can just substitute in. So need to knows. An exponential function is an exponential function, or exponential growth function, sorry, is one that increases. So it's when b is greater than 1. A decay function is one that decreases. So b is between 0 and 1. An exponential regression function use the equation of the curve of best fit when the scatter plot looks like an exponential function on both sides. So make sure that you check out the steps on page 66 for the regression. And it's choice, the last choice is choice 0, okay? So whereas you chose, you know, a certain number for linear, I think linear is 4, quadratic's 5, 6 is cubic, 0 is exponential, C is sinusoidal, but we're looking at choice 0 for exponential. And then you can use the tools we've learned in terms of graphing functions to solve. Okay.